Okay, let's unpack this. Today, we're diving into some truly mind-bending physics that proposes a completely new way to think about the universe.
Right.
We've been handed this fascinating set of documents, a paper called Coherence and Cohesion and Resonance Fundamental Equations Big Emergence.
Right.
And our mission really is to pull out the core ideas from this pretty dense material, give you a shortcut to understanding what might be a groundbreaking theory of everything.
Absolutely. This deep dive is all about trying to unify some fundamental aspects of physics, cosmology too. It reveals a deeper connection between concepts we thought we understood pretty well.
Yeah.
You're basically about to get insights into how order, how integrity is preserved across the universe. We're talking from the tiniest particles right up to the largest cosmic structures.
And what's really exciting, I think, is how these concepts like coherence and cohesion, they're actually tied into something much more fundamental, resonance. And this could really challenge our understanding of, well, everything. Gravity, maybe the origin of the universe itself, even things we think of as fixed, like universal constants. It feels like a journey into the hidden architecture of it all.
It really is.
So let's start with some familiar ground, maybe. When you hear coherence and cohesion, what usually comes to mind? Like a coherent argument or a cohesive team.
Yeah, those are great everyday examples, and they capture the essence. Coherence, in a general sense, it's about logical consistency, order, unity within some system.
Okay.
In physics, specifically, it often relates to the phase relationship between waves or particles. Think like laser light. It's coherent because the light waves are all in step, predictable, consistent, not like a jumbled flashlight beam.
Right. Focused.
Exactly. And in information, language, it's about clarity, logical flow, making sure all the parts fit together and make sense.
Got it. So that's coherence. What about cohesion then? How's that different?
Well, cohesion is more about the force that holds components together, the actual bonds.
Right.
So while coherence is more about that consistency, the logical structure, cohesion is the physical or maybe functional bond that keeps the system intact. You need both, really, for stability, for things to work properly. It doesn't matter if it's an object or an idea or even a group.
Structure and the glue holding it together.
You could say that, yeah.
Okay, definition's clear. But here's where it gets really interesting, right? This paper takes these two ideas and suggests this really profound connection to a third one. Resonance.
That's the core insight, yes. This theory looks at coherence as let's say, the order condition. And cohesion, that's the resonant condition.
Resonant condition.
Yeah, resonance is seen as playing this absolutely central role in maintaining structure, dynamics across all kinds of scales, all dimensions even.
Wow.
And the really crucial point here, the big leap, is that cohesion and resonance are considered functionally identical in this theory.
Functionally identical. So cohesion is resonance.
At a fundamental level, yes. It emphasizes resonance as this universal characteristic, maybe even of hyperspace, which we'll get to. Resonance is presented as the ultimate binding force. It ensures everything, particles, planets, galaxies, they're all connected, all aligned within this hyperspace.
The ultimate glue.
Pretty much. The paper puts it, let me see. It would be consistent to say that all cohesive activities in the universe are fundamentally resonant activities when examined at a deeper level.
Okay, so every force holding things together, molecular bonds, gravity, it's all just resonance playing out.
That's the implication. It's all expressions of these underlying resonant activities, a universe built on vibrations, essentially.
So we've got resonance as this universal glue. How does the theory then actually, build the universe from that starting point? What's the blueprint?
Well, it gets mathematical, of course, but the core idea is to define resonance as a fundamental operator, something that governs phase, frequency, harmonics.
Oh, okay, mathematical rule.
Exactly. And then cohesion, the forces we see, that's treated as an emergent property that just naturally comes out of these resonant interactions.
Emergent, meaning it wasn't there initially, but arises from the resonance.
Precisely.
Yeah.
And the goal then is to unify physics by translating all those different equations we have for specific forces into this single resonance-based framework.
Which forces are we talking about?
Oh, all sorts. Van der Waals force for gases, surface tension in liquids, capillary action. Then you've got Coulomb's law for electricity, Newton's gravity, even things like the Pauli exclusion principle in quantum mechanics, or the Madelung constant for crystal structures.
So all of those different equations.
The idea is, yes, they can all be seen as just different manifestations, different facets of these deeper underlying resonant interactions.
That implies there could be one single universal equation covering all of them. What does that look like? I mean, conceptually, what does it do? And how does that simplify things?
Conceptually, yeah, it's quite elegant. The equation basically says that any cohesive force, whether it's gravity pulling stars or molecules sticking together, depends on how a universal resonance function changes over space and time.
A resonance function, like a description of the vibration.
Kind of, yeah. It captures the phase, frequency, amplitude of the resonance.
Right.
And there's another part, like a stiffness factor, that depends on the resonance itself and describes how the system resists change. It varies depending on the specific interaction, but it's all linked back to resonance.
And that simplifies things. How?
Well, the advantages are potentially huge. First, universality. One equation framework instead of many different ones for different scales and contexts. That's a massive simplification.
Okay.
Second, predictive power. If this is right, it could predict totally new forms of interaction, maybe new materials where resonance is key, things we haven't even thought of.
Right.
And third, interdisciplinary consistency. It potentially links cosmology, material science, quantum mechanics under one theoretical roof. It's aiming for that grand unification.
That sounds incredibly neat, almost too neat. Are there parts of physics that maybe don't fit so easily into this resonance idea yet?
That's a fair point. The paper does acknowledge there are still puzzles, especially at, extreme quantum scales or inside black holes, perhaps. But it suggests pathways, ways this resonant framework could eventually incorporate those too. It's presented more as a foundation for ongoing work.
Okay, so it's a framework, not necessarily the final answer to everything just yet.
Exactly. And speaking of foundations, this theory goes even deeper. It suggests this hyperspace underlying everything. Hidden dimensions.
Hyperspace. Okay, now we're really getting out there. What does that mean here?
It means extending the math, generalizing to what they call hypersymmetry and hyperspace coherent resonance. Think of hyperspace as having extra dimensions, beyond our usual 3 of space and 1 of time.
Like in string theory, more dimensions.
Similar concept, yeah. A deeper, richer reality. And within this hyperspace, there's a more fundamental resonance function and a generalized stiffness function operating across all these dimensions.
And why add these extra dimensions? What does that buy you?
Well, the really fascinating idea is that the forces we know, like gravity, electromagnetism, the forces holding molecules together, they might just be projections, lower dimensional shadows, if you like, of more fundamental cohesive forces acting in that hyperspace.
Like Plato's cave, almost. We see the shadows, not the real thing.
That's a great analogy, actually. And it connects to order, too. The theory links negentropy, that's negative entropy, associated with order and structure directly to how coherent this resonance is in hyperspace.
So more coherence in hyperspace means more order in our reality.
Exactly. More ordered, more stable systems, both in our familiar space-time and in the hyperspace itself.
Okay, if this hyperspace exists and it's governing things, what could we actually see? What does it predict? Any surprising things we could look for in experiments or, out in space?
Yeah, that's where it gets exciting, because it does make some potentially testable predictions. Well, for one, exploring different hypersymmetric resonance states could predict new phases of matter, or maybe new types of molecular interactions we haven't seen, perhaps under extreme conditions, or in specially engineered materials.
Stuff we could maybe create in a lab.
Potentially, yeah.
Yeah.
Then there are particle physics anomalies. The math suggests these hyperspace modes, which could lead to new resonances or particles that standard quantum field theory doesn't predict.
So it could explain weird results from particle accelerators?
It's a possibility, yes. Yeah. Things that don't quite fit the standard model. And some solutions in hyperspace, stable, localized things like solitons, they could be candidates for dark matter, structures that exist but don't interact much with our normal space.
Okay, dark matter is a huge puzzle. That's interesting. Anything else?
Gravitational waves. Hyperspace resonance might actually affect how they travel, maybe causing distortions or echoes in the signals that detectors like LIGO or Virgo could potentially spot.
Little ripples from extra dimensions.
Something like that. It could also change predictions for black hole dynamics, how their event horizons behave. Maybe Hawking radiation, the gravitational waves they emit, might look different than standard theory predicts.
Wow.
And finally, it could mean new quantum states. Bound states influenced by hyperspace, potentially explaining anomalies we see in the light spectra from atoms or molecules.
So this isn't just some abstract mathematical game. It's suggesting concrete things we could actually go looking for or might even stumble across.
Exactly. It's trying to connect this deep theoretical structure to observable phenomena.
That really does change the game. It's not just finding the smallest bit, but tuning into the deepest frequency.
Well put.
And speaking of changing the game, this theory doesn't shy away from the big targets. It apparently rethinks things we thought were absolute bedrock, like the universal constants.
This is definitely one of the most radical parts. The idea is that constants like G for gravity or the fine structure constant alpha, Planck's constant h bar,
Yeah.
they aren't just arbitrary numbers plugged into the universe. They're not fundamental fixed values.
Not fixed, but they're called constants.
Right. But here, they're seen as emergent properties. They arise naturally from the deeper structure. The paper calls them hyperharmonics.
Hyperharmonics, like resonant frequencies of the universe itself.
Exactly. Resonant frequencies within the overall hypersymmetry of the cosmos,
Yeah.
emerging naturally from the mathematics of hypergravity and coherence.
Wow.
And it gets even stranger. It introduces something called the anthropic operator.
The anthropic operator, like the anthropic principle.
Related, but framed differently. It's proposed as a mathematical object that modifies the coherence and interacts with hypergravity, specifically to ensure the constants end up with values that allow for complexity, for structure, essentially for conditions conducive to life.
So it's not just luck that the constants are right for us. The universe kind of nudges them.
That's the suggestion. It interacts with the fields to give rise to the G, the alpha, the H bar that we observe. And it implies these constants might not be perfectly constant everywhere or every when.
It could change.
Potentially, yes. Maybe over cosmic time, maybe near black holes, perhaps in the very early universe, or even in high-energy collisions where coherence might fluctuate.
Mind blown. Okay. And if rewriting the constants wasn't enough, it also takes on the Big Bang.
It does. It offers a critique of the standard Big Bang model.
What's the critique?
Well, the usual points. The standard model doesn't really explain what triggered the bang or what came before, if anything. The whole idea of an infinitely dense point, a singularity, is mathematically and conceptually tricky.
It's a singularity problem, yeah.
Right. And while inflation helps with some issues, it needs some fine-tuning itself and doesn't necessarily predict new things easily. And then there's that fundamental question. What about before?
So what's the alternative here? No Big Bang.
Not necessarily no Big Bang in terms of expansion, but a different origin story. Instead of a single singularity, imagine the universe emerging from an infinite field of hypergravity.
Infinite hypergravity.
Yeah. And through localized, coherent emergence events within that field. These events create pockets of matter, energy, structure. They call it a multi-coherent event origin.
Multiple events, not just one bang.
Potentially numerous events, maybe happening simultaneously or in succession. It avoids needing that initial problematic singularity. It's described as scalable, maybe even ongoing. The universe is a mosaic of these emergence events.
Wow.
And a really crucial insight here. Matter itself isn't fundamental in this view. It's not an inherent property of particles.
Matter isn't fundamental. What is it then?
It's an emergent property. It arises when these coherence-infused resonance points interact with or bind to the hypergravity field.
This sounds almost alive. The source even talks about matter being a holographic projection. That's hard to wrap your head around.
It is a very different perspective. The holographic idea suggests that the matter we touch and see are solid, tangible reality. It's like a projection, a lower dimensional representation of the higher dimensional nature of hypergravity.
So the real stuff is the hypergravity field.
In this view, yes. Hypergravity is the core reality, the substance from which matter emerges. It completely challenges our usual view of the physical world being the ultimate reality. The most real stuff might be beyond our direct perception in that hyperdimensional realm.
Leading to a unified view of matter and gravity.
Yeah.
Because matter comes from hypergravity.
Exactly. And this ties into the resonance points and the birth of matter. These points are fundamental nodes of coherence where energy and information meet. Building blocks.
Okay.
The key step is when they bind with hypergravity. That's when they acquire mass, transforming from just energy or information into what we perceive as physical stuff.
And does this say anything about why there's more matter than antimatter?
It provides a potential basis, yeah. It suggests these resonance points might just have a statistical preference, maybe a slight asymmetry in how they bind or form, leading to more matter.
Okay, so if the Big Bang wasn't a single starting point, what does that mean for the universe's overall structure and how we interpret what we see out there?
It definitely suggests a different cosmic map. Instead of one universe expanding from a point, you might have local universes or these large-scale emergence events happening within a much bigger background, maybe an omniverse.
Local universes. Like bubbles.
Sort of. The paper points to structures like the Laniakea supercluster, which contains our own Milky Way. Maybe that's our observable universe, the result of one specific emergence event from this underlying hypergravity field.
Our entire supercluster as one event.
That's the idea. Or even bigger structures, like the recently discovered South Pole Wall. Maybe that's another, even larger emergence event. It suggests a kind of hierarchy.
So Laniakea could be inside the South Pole Wall event, potentially.
It's conceivable within this framework, yeah. It challenges that single origin story and suggests maybe the cosmos is much more diverse, maybe different regions born from different events could even have slightly different physical characteristics or constants.
Wow. And if the origin is different, does that change how we interpret things like redshift, the evidence for expansion?
It offers a potentially complementary perspective on that, too.
Complementary, not replacing the Doppler effect.
Not necessarily replacing it entirely, but suggesting another factor might be at play. For redshift, the theory proposes that some of it could be caused by light interacting with huge clouds of matter or mass distributions out in space.
Light losing energy as it passes through cosmic dust and gas.
Something like that. As light travels through or maybe reflects off these massive structures, it could lose energy, shifting its frequency downwards towards red. This would imply that denser regions might show higher redshifts, even for galaxies moving at the same intrinsic speed.
And blue shift.
Conversely, blue shift could be caused by processes that increase the light's frequency. Maybe refraction or gravitational interactions as light passes near a very massive object, giving it an energy boost, a frequency upshift.
So it adds another layer to interpreting redshift and blue shift, on top of motion and expansion.
Exactly. It aims to complement the standard model, maybe explain some anomalies or variations that aren't perfectly accounted for just by Doppler shift and cosmic expansion.
Has this idea been tested or checked against observations?
Well, the source itself does a critical assessment. It notes the idea has logical coherence within its own framework, and it could potentially explain some weird redshift observations.
But
it faces a big challenge from the enormous amount of evidence that does support the standard Doppler effect and Hubble's law interpretation of expansion. Any alternative like this really needs to explain all that existing data, plus make new specific predictions that could distinguish it.
so an intriguing idea, but needs more work and evidence.
Definitely. It makes you wonder what else might be encoded in the light from distant stars, though.
Absolutely. So bringing this all together, what does it mean for us, for our place in all this? This isn't just physics. It feels like it fundamentally shifts the philosophy, our understanding of reality, symmetry, maybe even free will.
The philosophical implications are really profound, you're right. Take symmetry. It's always been key in physics. Hypersymmetry suggests an even deeper, more fundamental kind of symmetry that operates across these hidden dimensions, binding everything together. It implies a universe that's far more unified and interconnected than we usually think.
More connected, okay.
And the structure of reality itself. If our familiar 4D reality is just a subset, a projection from a larger hyperdimensional reality where hypergravity rules, well, that fundamentally challenges what we consider real. The tangible world might not be the ultimate layer.
It makes you feel very small, but also part of something much bigger.
It does. And then there's determinism and free will. If there are these deep symmetrical laws governing everything from hyperspace, does that lock everything down? Is it all predetermined?
Yeah, that's a big question.
Or does the sheer complexity, the multidimensionality, allow for emergent phenomena, things that aren't strictly predictable from the base laws? Maybe that complexity creates space for genuine free will, for agency, even within a broadly deterministic framework.
So maybe complexity itself allows for freedom.
It's a possibility this framework opens up. And causality, too, might not be a simple A causes B chain, but a much more tangled web across all these dimensions.
This is, mind-blowing is the word. It really makes you question everything you thought you knew about how the universe works and our place in it. It's like finding out the stage is infinitely deeper than you thought.
It's a radical shift in perspective, for sure.
Yeah.
But one grounded in trying to unify physics through coherence and resonance.
Well, we have certainly journeyed through a remarkable theoretical landscape today, from resonance as this universal glue to matter as a hologram, even questioning the Big Bang itself.
And hopefully you now have a unique handle on this unified framework, how it attempts to tie together constants, matter, cosmic structures, all rooted in coherence, cohesion, and this idea of a deeper, hyperdimensional reality.
It definitely leaves us with a huge question to ponder. If our universe is just one emergence event among potentially many, defined by this invariant hypergravity and emergent constants, what does that really imply about existence itself? And just what discoveries are waiting if we start looking for these invisible threads of hypergravity and coherence?
It's a profound thought. This framework doesn't just try to simplify our models. It reinforces this idea of resonance as a truly universal principle, active everywhere, intrinsic to the fabric of hyperspace. It points towards a cosmos far more interconnected, meaning far more subtle than we can currently grasp.
Keep asking those big questions. We certainly will.